So we have to look at this thing here. Okay, now the degree of the freedom is n minus 1. So it's your sample size minus 1. That's a degree of freedom, okay? So here we took half of alpha, right? And now we're going to use this student t-distribution. So let's see. If you have an n greater than 30, you can go directly to use the normal. But if you're around less than that, you want to use this t-distribution. So the t-distribution is this. Now, that should look kind of familiar. It started like we used to have z's, but now we have t's. It's x minus mu divided by s divided by the square root of n. So it looks like a light. It's called student t-distribution of sample size n. So we have our degrees of freedom. So let's say an example of 10 scores have the restriction that their mean is to be 80. We can freely assign values of the first 9 scores, but the 10th score would be determined. We have, but it says, but the 10th score would then be determined. So we have what they call 9 degrees of freedom, which would have been 10 minus 1. Okay, now let's find this critical values. What are the critical values? Well, when we had this, and we had on bell curve that standardized, right? So that was over there at mu equals 0, and a sigma would be equal to 1 that way and this way, one deviation, 1. So on these things, when we figure out how much we want under the table, remember what's under the table is alpha divided by 2. Alpha divided by 2. Where did I get that? Because 1 minus whatever confidence interval you're equal to, what you want is considered alpha. That's the letter alpha, Greek letter alpha. So if it's 0.05, like if I have 95% confidence, right? 1 minus a 95 would be what, 0.05, yes? And then half of that area for two-tail would be, you can see here that it would be, inside would be a 0.025, yes? And a 0.025, okay? Now I looked at my table for in the guts, and I worked backwards. I got a 1.96 here and a 1.96 here. Okay, that's the z critical values. Okay, so we're going to have the same thing with the student's t-distribution, just going to be a little wider spread. And we're going to still have the alphas, right? Alphas subdivided by 2, but these are going to be t critical values because we're doing it from a different distribution. Okay? And to do that, we have to look, okay, so let's try it. Let's find one that says finding the critical values. Not z's, but t's. And here, what did we do to take it? Remember, not when it started, it was not a 0 mean, right? It was over here. So we had some score x here, but to convert it over to a z-score, remember we had z equals x minus x bar divided by sigma. Do you remember that? That's how we take this x and turn it over if we wanted to turn it to a z. This also has the same thing, but you remember the formula was a little different? I'll show it to you here in a second. Okay, so now let's try the table. So this is A3. So we got, how much we have in here in the tail? How much is inside? Well, they want what degree confidence? 10 minus 1. Where's that? Oh, no, that's degree of freedom. So our degree of freedoms is going to be 10 minus or 9, okay? But I'm talking about what percent confidence we're looking for. 95, 90, you know what I'm saying? What is it? Let me go up here and see what they're asking for. I don't know if that they want me to construct something. Oh, look, this is what they use. This is equation x minus mu divided by s divided by square root of n. You see? Instead of a z-score, you get a t-score. Okay, so let me see if they want... okay, that's okay, but I just don't know what alpha was in this case. So let's take a look at the table. So then they have student distributions for different sample sizes. And then here we have n equals 3. or n equals 12. So let's see how they do. No, I have that table over here, I think. Okay, so if I look at this and I know that there's 0.025, it's right there, see it? 0.025. And then these are the degrees of freedom. And at least the one we were talking about, 9, right? Go over here, below the 0.025, you see that? That's 2.26, let's say, 2.26, yes? So now when I come back to here, okay, so here now, notice that I had 1.96 here, but what I got here now is what? I went 9 degrees of freedom under the 0.025 is 2.26. And this is minus 2.26. Now look, it went up, it's a little wider than this, isn't it? Because it's allowing for more variance for the fact that you don't know something. You don't know the true sigma. You understand? It looks weird, but that's what it is. So this is what's in the tail right here. And that tail is on your first row. And then you go to the degrees of freedom to find the T critical value. Does anybody know what I'm talking about? Okay. Well, maybe in time. All right, so let's go back here. Okay. Next. Here we go. Here's a standard normal distribution. Okay? Do you see it here? The standard normal is the green. See it? Now, the student T distribution with n equals 12. Do you see how it starts to get wider? It goes beyond. It's kind of stretched out a little bit. And then this was the student T distribution. This is a student T distribution with n equals 3. Well, n equals 3, it even spreads out further out faster. Why? Because you have less data points. The more data points you have, the better survey is of your population. Any questions? No, it's too easy? Oh, gosh, okay. I wish I was a genius. All right, now, let's try it. They're telling you that's what I was looking for. We want a 95% confidence, right? So what's alpha? 0.0 what? 0.05. Yeah. So alpha divided by 2, 0.025. Okay. So then we have n equals 15. Okay. So we have n equals 15. We have degrees of freedom, which is n minus 1, which is 14, right? And we know we're using a T distribution. And so we have this, as we said. And now we have T at 0.025. Yeah? And we said when we came over to here, right? There's the 0.025. How many degrees of freedom? 15. You see what we got here? So it's is it 13 or 14? 14. Okay, so 14. And I think it's just 2.1444. Yeah. That's a critical value. So that would be, okay, so there, 2.145. That's on this side of it, right? And now we go here. And there's the 0.2025 in there, and we need to calculate these critical values. Well, we did, right? Okay, so now what? Now ready for the confidence interval? Okay, let's do this example. So, ectograms. This is a weight in ectograms. I think that's units of 10. Randomly selected girls at birth based on the data from the National Center of Health. Here's a place to get information, too. Here's a summary of statistics. N is that. X bar, they're telling you. S, right? What is S? That's your sample. That's my sample deviation, right? Notice that I don't have a sigma. The sigma is not known. Only God knows it. In the previous one, they gave you a sigma like God was, like you got that. So now, use the sample data to construct a 95% confidence interval of the weight of these girls. This is what was selected, the weights, right? If it were purely random, we'd have no pattern to look for. You see, everything I do, I like to look for patterns, okay? Even in my art. So I go like this, It's not my art. I'm just figuring out how the masters did it. There's no real book. So we first verify the requirements are satisfied. The simple, let's say 2, because the sample size is n, is 15, right? Remember, if we were greater than 30, we could use the normal distribution because it's getting big enough where that little wider part doesn't matter anymore. I don't know if that makes sense. Okay, and I don't know why they do that. Though they're using the technology to just check to see how normal it is. It's not too normal. It doesn't look like... Okay, so we'll use the technology too. Let me just see what they've done here. Okay, now, what do we do that's so bold? We take God's truth that we don't know, and we make a confidence interval about it. Okay, so confidence interval is that here we have the mean. Actually, that's probably where we need to go. So here we have the mean, the sample mean, the error term. It already calculates it out for you, the plus and minus error term. And here are the limits. That is that's going to be here. Look, 29.2 and 32 point. Yeah.
How do we do that one step?
Oh, you want to do it? You want to do it this crunch way? Okay, we'll do that the crunch way. But we'll first see what it is uncrunched. Okay, now the error term is equal to whatever this was. Remember, it wasn't 1.96. It was 2.14 or something, right? And then we do know what S is, right? That's from our sample, and we know that. Okay, so we got 2.54. So we got an error term of 1.606, okay? And so if we were doing it the old way, we're going to take mu, right? It's going to be equal to what? What would we use? Well, like x bar, right? Plus an error term, and x bar minus an error term, right? Because x bar is our best estimate of mu. All right, so here we are. Look at what we're doing with God's truth. Mu is right here. Here's man-made mean minus error term, mean error term. Remember, this error term has the t distribution coming in it. So that we have the mean, which was 30.9 minus 1.6 and plus 1.6. So there we got the confidence interval. And interpretation is right here. Let's see, we might be able to do the same one on StatCrunch. So we are 95, this is interpretation, we are 95% confident that the limits of the lower bound, 29.2 and hectograms and 32.5 hectograms, actually contains the value of the population mean mu. We're 95% confident if that's the case. So if we were to collect many different random outcomes, right, of these many, and 15 newborn, we're going to find the mean weight to see the mean. Now, the mean weight is above 95%. The resulting confidence would contain the value of the mean of all newborn girls. So you could go out there and take a sample, right, like we did of these girls. Go out, take another sample, another sample, another sample, another sample. We would expect that that new mean will fall between here and here with 95% of the time. So if I'm making a guess, I'm going to bet on the side for 95%. See if we can work that on that StatCrunch. Okay, so what data is this? Oh yeah? Yeah, but I'm trying to find what one of these. I don't know what data set if we have it. Okay, refer. Oh, this is a problem. Well, this is easy enough because they're asking for degrees of freedom, right? So this one already gives us our t distribution table. N is 50, right? So I don't know that this. Yeah, I don't know that really is. Oh, good. I'm trying to. Okay, now t sub alpha over 2. Well, that we want 95% confidence, yes? So again, when we go here, we want in the inside here is 0.025, yes? Half of the alpha. And over here we have, if we're talking about two tail or one tail, if it's all on one tail, you're going to put the whole 0.05. This is not divided by 2 if we're doing just a one-sided table. So depends what they're asking, how they're asking. I'll look again. So in this case, in that case, we have 0.05, right? It says, so this is area in one table. So here's 0.05. And the degrees of freedom are what?
49.
I should have stopped right there because we can use the normal curve. But anyway, so it's going to be, I don't know what you do there. It skipped from 45 to 50.
So when I do a problem like this,
Oh, here's two-tail. Okay. So if we have 50 instead of 45, I don't know. So then we want, but actually we could go right into the bell curve because it's over 30. But even if you wanted to estimate, then that was the, see what were we looking for? In one tail, or here's for two tails, and this is one tail. So I don't know which, and then that one came down to 50. So it's like 1.22. All right, so what's that do? On the right here. Oh, round to 2 decimal places.
Yeah.
Well, I don't, that's all I had, wasn't it? 1.22. That's two tail.
Nope, about the 0.
0.25. So if it's, well, anyway, if it were, let's say we go down to 50. So where did you get yours? One tail, 0.25. Well, this says alpha. That's why it was confusing. It doesn't say alpha divided by 2. Oh, if they mean alpha divided by 2, then it's like a two-tail. That's 0.05 with 0.25 on one side and 0.025 on the other.
Yeah.
So if you take that one down to 50, so then they just put 2?
2.0.
1? Oh, 2.01. Okay, so it was 2.01?
2.01.
Oh, I keep doing that. 2 point. So it's still different than 1.96. Okay, so let's take a description of what it means for number of degrees of freedom. So the number of degrees of freedom for the collected sample is the total number of sample values? No. You got to subtract one, right? The number of degrees of freedom of the collected data is the number of unique non-repeated values? No. And the number of samples determine a certain restriction has been imposed on the data value. The number of degrees of freedom of a collection data is the number of samples values that vary after certain restrictions have been imposed on all data values. Shoot, I don't know. Collect D.
Printing them all out and like keeping track of
Good idea.
information.
There you go. Okay.
Like that person.
Yeah, but it's not really what I wanted to show. I wanted to show how we can use the StatCrunch now. So I'm done with this one anyway. That was, okay, yeah, that was, I don't think it's, I'm trying different things. Okay. That was the simulation for a sample size 100. I don't know. There's the confidence interval 95. And then, I don't know if this, but this is for 100. I don't know why it's doing it. There's no analyze here. Okay, it's just a window that opened up. Let me just see what this one is. We got a mu and a sigma. So remember, we use the t-distribution when? When would we use a t over a z distribution or normal distribution? Yeah, and also what if sigma is not known? Yeah, sigma not known, so we're going to use our s instead. So I was trying to see what example this is to see if we have it. Is it talking about find the critical values? It doesn't talk. It says using technology. Let's try that. Okay, using technology, we can find that for 14 degrees of freedom with an area of 0.025 in each tail. So let's see if we can, is that what you're looking for, like with technology? The critical values or what? Or the whole thing? Okay, wonder if, see, so remember we have a degree of freedom of 14. We have two tail, we have a 0.025 in the area. Let's see what we can do with that. So now I want to go and It says, where do I have, that's e-text. Here, how do I clear this out? Everything's a new challenge. Okay, so let's see here. So let me see on data. Okay, and stats. Let me see if we got covariance. Let's see. We don't have any columns or rows, right? And in graphs, confidence interval. Is this a proportion? It's about, we're talking about P or mu? So it's for a mean, isn't it? Yeah, okay. So let's see if we go like here. Oh. Well, I guess that doesn't. Did we want 95% confidence? The sample size is what? What's the sample size?
Last problem it was 50.
Yeah. That's the one I'm talking about. 50. Okay, and what is the mean? Does anybody remember? You have it? Or you don't have it? That's a book. Yeah, I can get it. Let's see. I don't know if I... Yeah. This one here. So what was the mean? N is there. Degrees of freedom. Let's see. Do I need this guy or this guy? Okay, here we are. Somebody want to write that down because I'm going to go. Okay. And then S is we don't know sigma, but we know S. Yeah. So now let's go back here and here. This thing is, there's got to be a way that I can, well, it used to be a keyboard there. Could not start on. So anyway, we go back here, and that was how much? 30.9. So let's go back. So we got 30.9, and then we have the standard deviation was what? Okay, and then, so here, look. This is z-score sample, and then we have an S deviation. Or we left it at T. Or you can do, see, now this is when you do know sigma. And you can use Z, and here you can use Z again, but, so let's see what we got here. I go like that. Okay, so now I got, let's see what that just does it again. Here, oop. That's a weird way to do it. There. Do you see the upper and lower limits? Is that standard error and mean 31? Why is that changed? I don't know. Does it matter where I'm at? Oh, look here. That's each one, or what was the? What is the lower? What does it say? And on the book, does it have an answer? Oh, we'll go back here. Let's see. I'm trying to figure out what I'm doing. So I close here. So see, each one of these has that. So I went to this thing, but I don't know why. What are these? Oh, this looks like it was ran 100 times. Well, what if I picked the actual data itself? So I went to, let's see, stats, summary, columns, and then, well, this is not asking. Oh, upper and lower bound. Oh, I don't know which one I was looking at. What were? But what was the data? I don't have data, right? Okay, so what was this area here? This is the lower bound and upper bound. And this is row 1? Oh yeah, row 2, row 3. Oh. This is there. Okay, what was the sample mean? Each one came out differently, a little bit, right? This is ran 100 times. So if we did it one time, or do we do 50 times? No, one time. Would this be it then, the upper and lower boundary? Let's see if that's right. 31.86 and 30.92. It seems like it's the hard way of doing it, if it does. Let me see what we have here. And that was here. It says, well, we could have used the normal curve, but let's keep going. This is birth weight. Oh, that's what I got. And then the lower limit was, I'm looking at this. Okay, remember this right here, 30 and yeah, and then yeah, that's the upper limit, the lower limit, right there. And so I had it. Was it here? Yeah, so I had. Oh, the lower bound. 29, and what's the other one at 30? Oh, here's the lower bound anyway. They got it confusing. Yeah. Why do they have so many lower and upper bounds here? Oh, maybe it has to do, no, I have no idea. So here's sample mean. That's true. That's what it was, wasn't it? 30.9?
Yes.
And the lower bound was what? Well, I guess that's the closest we get. That'll go to 29.1, right? And then it depends where you cut it off. And what was the upper bound? I don't know. Would that go to 32? That would go to 32, right? How many places are we rounding back to?
I was just doing one, because they had.
Oh, here?
numbers.
So that looks like about right. Yeah. Why don't we get the same? Now here's, oh wait, I'm looking here. There's upper and lower here. That was a sample mean. So it's 29.24. Okay, and that was 29.24, 29.24, 29.24. And this one, that was right here. The upper bound. Oh, this is a different sample. I mean the mean. It starts over again. So here it is right here, right? Why did I use this? Because this was just one simulation at one time.
So that's where we should be looking.
There's probably a better way, but I know this is it. Now, if you kept running it each time, now this comes back around again, and then you did another mean, right? So it's like two columns. So this is the upper and lower bound, right? It's going all the way down. And so, but the sample mean that we had was 30, well, that's the same ones, isn't it? Oh, it's the same number too, isn't it? What's going on? 30 to 31. 29 to there. Now I don't know. You would think there'd be an easier way to do it, but you'd have to have the actual data. I don't know, because this is just the mean, and this, we don't have the actual data, do we? But we kept running it, and that's good. It's a simulation, and we saw this thing. Yeah, that was for a mean, right? And I left this distribution here, and that one had changed, right, to 50. And this too also had to change, right?
Yeah, that was 30.8.
Yeah. Now this is saying a normal, but right here it says t interval. So I don't know. We'll play with it and see what happens. Let's go back. Okay. So anyway, we got this one okay, 2.14, and then it was 2.9 divided by the square root of 15. Is this a different problem? Where's this 15? Is 15 and not 50? Oh, that's right. Where did I get 50 then? I got all screwed up. Was that the other problem? I don't remember now. I thought I had 50 because we had degrees of freedom of what? We used 50, I thought. This is 14. 1 minus 15. Well, anyway, play with it.
Yeah.
We'll see what goes on. Okay, now. Oh, we're done, huh? Dang it. Okay, that went fast. This was, remember, we can estimate these things by using the upper and lower limits. It's like an average, right? That's cool. Smokers, and then exposed to smoke and not exposed. Levels of what? cotinine. Let's see what we got here. Okay, now this one, I think we went over this before, but this is if you wanted to, you're going to do your project, and you want to know how big a sample should you have. Well, what's it going to depend on? How confident you want to be. So the more confident you want to be, so find the sample size. So here's our notation. This is from a bell curve. This is your error term. And so this, we can actually calculate how they got to this, but right now, the sample size should be the z sub alpha divided by the sigma. In this case, sigma is given. Divided by the error term squared will tell you what sample size you need. Right? Now, where does the confidence interval come in at the 95%? When that alpha divided by 2, that z sub alpha divided by 2 takes into account the z value, right? So if you set your confidence interval to 95, right, that's going to be 0.05 divided by 2. But if I set it for 90, that's going to be 10, right? So this is varying according to how tight we want our confidence interval. And I think that should, yeah. Now here's what sigma's unknown. So in that case, we had to use the degrees of freedom. Now that one we do have. That might be worth working because I know we have IQ scores, I think, in statistics. So assume that we have estimate IQ scores, okay, and that we want 95% confidence. It says with a sample mean and a 3-point IQ variation population. Let's see, the sample mean is within 3 IQ points of the population mean. So we should take a sample of 97. If that drops to 90, you expect this number to go up or down? Does this number go up or down? Do I have more or less area in the table and the tails? More area in the tails, right? So I would expect that it'd be, well here they got 1.96, right? That's 0.025. But if I do 10%, would you expect this number to go up or down? The 1.96. No, here we go like this, right? And then we have, in here we have alpha, right? Divided by 2. So if that was 95, we know that, but if it's 90, what do we have? 90%, right? So we have 0.01, 0.10, and then we divide that by 2. That means this area is bigger this way, right? Don't you agree that this is just 0.025, but this one's 0.1. This is 1.96, so I expect this number to be smaller than 1.96. Do you see it? Yeah, you're moving sort of towards the center, right? Here was minus 1.96, but now you're less confident, right? So you have more like error term, if you will. And so that I would expect that these numbers would be less than 1.96. I guess that's it for now. Any other questions?
For the break, or
Oh, I hadn't thought about that.
I can start researching.
Well, what you can do is we'd have to go to the hypothesis testing.
So we gotta wait.
Yeah, I think so. That would have been a good thing to use that week. I hadn't thought about it. Well, you can try it, though, if you want to see if you can figure out Chapter 8. Because that's the hypothesis testing, and then find a data set according to which distribution you think it is.
They just all have more time now.
I know, that's the thing. You don't?
No.
Oh, you need to teach. Oh, okay.
Yeah.
Okay. Next, we'll be asking about sigma itself. We're trying to put a boundary between God's true deviation. And it has a chi-square distribution, not bell curve. So we have another table to put.
Yeah, that chi-square was kind of freaking me out when I was trying to figure it out.
Right, that's chi-square. It still has degree of freedom, right? But they're skewed to the left. So now we have to worry about how we put in our tail here. Right? So you can see what's happening as the degree of freedom's going down. You're just pushing over here in that way. And that is the chi-square distribution. So, but we're still looking to put a boundary around God's truth, right? But this time, the parameter that we're trying to put a boundary around is going to be, here's 0.25 and put 25. And now we have the x critical value to the right and left. Now, this one is that we use degree of freedom of 21, and then use the degree of freedom. So we're accumulating from left to right. Yeah. So 0.95% is what? It's from here back. And this one is from here back. And then, well, she already used the table, but we'll get an idea of how to use that table. But I wanted to see if they're putting the error term around there. So let's make sure we got, I want to see if they're setting up a confidence, and here it is. Right there. That's the confidence interval for the real population parameter sigma. Why is these square root? Because they took the square out. So these had to be square rooted. So that then is my critical. That contains the error term and everything that you need. And you notice how it's not, you remember that we had x bar plus an error term? And here we had x bar minus an error term. Well, we don't have plus and minus, but we still have our sample deviation on both sides. So it's still being bounded by Mann's sample statistics.
Yeah.
Okay?
And then you also don't have your mean or your.
Well, not now, because we're talking about strictly the deviation, not the sample mean. That's why we're not using it. Okay, I guess that's it. Yeah, that would have been nice to be already at 8. I think generally that's my whole life. I'm running behind.
They said, gates are frozen.
Well, they opened up as soon as I got there. Yeah.